So we'll now look at yet another experiment which will give further support to the wave nature of light. So this is a simple arrangement which is to show interference of light. So let me briefly explain whatever you are seeing. This is a sodium vapor lamp, and then the light from the sodium vapor lamp is incident on this glass plate which is placed at an angle of 45 degrees to the vertical. So the light will be reflected vertically downwards. It will fall on this, this is actually a plano convex lens with the curved surface on the bottom. So there is a thin, when I place this over here, there will be a thin layer of or thin film of air between the lens and the glass plate which is at the bottom. So there is a thin layer or thin film of air of varying thickness because you have a curved surface. So when I keep it over here, the light which is reflected from this glass plate, the 45 degree glass plate, falls vertically on the lens which is over here, and then what happens is light is reflected from the bottom of this lens and then the top of the glass plate below. So these two beams will then interfere to form an interference pattern, and then this interference pattern, because of the circular symmetry of the lens, will be in the form of bright and dark circles. And of course these rings, Newton's rings, are going to be very small. You will have to see them through this microscope. Okay, the first thing is, in case you just see through this and you do not see any rings, then there could be a couple of things which can be wrong. One is that the light from the source is not incident on the lens. So adjust the position of the lens till you see that the field of view is bright, and after that you can adjust the focusing on the microscope. If you still do not see any rings, that is probably because you are far away from the center of the ring system. Okay, now I have adjusted it such that your cross wire is right at the center of the ring system. The center will be dark because of destructive interference. Now again, it will be difficult to see the rings through the microscope. So what I have done here is I am showing the rings here. Okay, this is roughly what you will see. As I said, the center will be dark, and then there will be alternate bright and dark rings. So what you have to do is, first of all, once you have located the center, move the microscope by using this screw over here. If you rotate this microscope is going to move. So you move it, and while you are moving, you count the number of rings. So that, let's say, you make the cross wire tangential to the 10th ring. So make it tangential to the 10th ring, and then you will have to note down the position of the ring by looking at the main scale and the vernier scale over here. So you might have to use this lens. It's very tiny scale, so you will have to look through this to note down the readings on the main scale and the vernier scale. So what you have to do is note down the position of the 10th ring on the main scale and the vernier scale, and once you have done that, you move this screw, rotate this screw so that the microscope moves, and then of course all this while you have to keep looking through this and count number of rings. So you move it till the cross wire now coincides with the 8th ring. So note down again the position of the 8th ring. In fact, you can take the position, note down the position of every alternate ring. So let's say you started from the right side of the center. You noted down the position of the 10th, 8th, 6th, and so on, all these rings. Then you come to the center. Then keep moving in the same direction and note down the position of the 2nd, 4th, 6th, 8th, and 10th rings on the other side. So that means throughout the experiment you are moving in only one direction. Now it might happen that sometimes while rotating the screw you reach the end. That is, now if you see, the screw has gone completely inside, so you can't rotate further. But then your experiment requires you to move in that direction. Then what you do is you can loosen the screw. So now I have loosened the screw, there is no connection. What it means is there is no connection between the microscope and the screw. The connection is lost if I loosen the screw. So now I can pull the screw out. This doesn't move the microscope at all, but then the screw is released. I can pull it out. So now I can push it in further. What I do is I lock the screw again and then start rotating it again. So which means I can move further in that same direction. So keep in mind that you have to move always in the same direction throughout the experiment to avoid the backlash error. If you move back and forth, there will be an error because sometimes what happens is backlash error means I am rotating the screw but the microscope is not moving, or there is a slip between the scale and the screw. So that causes some backlash error. So once you have what you are effectively doing in this experiment is by taking these readings corresponding to the various rings, you are noting down the position of the rings. And let's say for a 10th ring, you note down the position on the left side and the right side. You take the difference between these two, that gives you the diameter of the 10th ring, divided by 2 to get the radius, and this can be substituted in the formula which relates the radius of curvature of the lens, the radius of the ring, and the wavelength of light. So using this relation, you can determine the radius of curvature of this lens. So this is a very sensitive method to determine the radius of curvature of this lens, of the curved surface of this lens. And this method of determining the radius of curvature is very, very superior compared to mechanical methods of determining the radius of curvature. So all the optical experiments usually have a sensitivity of around micron, so which is much superior to mechanical means of determining lens or radius of curvature.